So, hello again, and it is my pleasure to announce that the next talk will be given by Ramadevi Pichai from Indian Institute of Technology in Bombay, and it will be about knots, topological strings, and quivers.
Thank you so much, Piotr. I've been having a wonderful time. I've been here for nearly 2 months now. A lot of things I've been learning. I know the group here and others in the participants and speakers have been working on quivers, but let me tell you from my perspective what all we have done, and then Pedro and Helder will take over and they'll say more details about it. Are you able to hear me? Yeah, okay. So this, I chose this mainly to give you a brief recap of these details have been already discussed in the initial pedagogical learning workshop, and also I gave a set of series of lectures on the computational aspects, focusing on how to get the knot polynomials and three-manifold invariants. So what I thought is that since there is a mix and match of audience, I'll give a brief recap, and then the focus of this conference on knot homologies kind of made me think that I should present the importance of homology, the categorification scheme initiated by Kovenov, and the other colored homology to give meaning to those integer coefficients in the Lorentz series for the Homfly-Petit polynomial. Of course, there is a physics approach. Both of them happened around the same time towards the turn of the century. So let me, and this was in 2005 or 4 where they could actually get a clear clarification of this. What categorification means on the Homfly-Petit using this. Are you all able to? Maybe I should stand only here. Okay. So these works were at the level where they could look at the partition function or three-manifold invariance, and so here it was only in the context of partition function on S3 and also the knots in S3, where they could get a meaning in the topological strings. But we would also like to see from what I had talked about surgery, you also listen to yesterday's talk, the surgeries can be done to get other three manifolds. Can we understand then within the topological string duality, which was the main focus of this work. So I'll try to give you a brief feel of what all I've tried to do to connect with the information where these are just done in 3D, 3 dimensions, and how it gets extended when you go into topological strings, where there is a target space which is a Galois 3 field. Of course, a lot of conjectures on the integrality properties, especially what we call it as Labastida, Marino, Uguri-Vafa integers, can be given proof from this quivers associated to the knots, and which broadly was initiated by Piotr and various other people from 2017 who are all here. So this gave a proof for those integer coefficients that the LMOV integers are actually integers by connecting it to the Donaldson-Thomas invariants. Okay? So what we focused was to find for some families, and especially for a double twist knot. This was also one of the examples taken by Abhishek, which is the double twist knot family, where we could give a algorithm of finding them. Of course, I'll end with some interesting, challenging open problems and ongoing works. Okay, so this is just to put you on a kind of a flow chart of the broad classifications of knots and links. Interestingly, these are arborescent or tree diagrams, you can call it. These are like the call it like a Feynman-like diagrams. And this is a very shorthand notation where you can see that each one is a finger, okay, and then there is a 4-valent vertex here. If you shrink all those 4 strands together, it becomes like you tell how many crossings are there. The bar is for the anti-parallel, and minus is if it is left-handed, and so on. So it is very neat way of showing a 4-finger diagram. Yesterday there was a pretzel with only 3 fingers, which corresponds to just putting a trivalent vertex. Okay, so this is a very shorthand way of drawing any knot, is what we would have thought, but only a class of knot called arborescent knots can be drawn this way. Okay, not just 4-valent, you can have multivalent vertex, and they translate in Chern-Simons theory as looking at a 3-ball with 1, 2, 3, 4 as 2 boundaries. So we know how to compute the states for each of these, and then we take an inner product and find the invariant. This is what I was teaching in the series lectures. Because all knots cannot be drawn this way. That's why they are arborescent, and then there is a non-arborescent. Of course, all knots can be drawn this way. Computation becomes easier if you redraw it this way, and that we can do only for arborescent knots. So non-arborescent knot, one of the simplest example, 8-crossing knot, we cannot redraw it this way. So this is a non-arborescent. So we need methodology to work out polynomial invariance for arborescent, which is much easier, and non-arborescent is a little tedious, but this has been, there is, I would say that it's progressively we are making some interesting, getting results for the invariance. Okay, so what is the essential way in which we compute? Suppose you are given a knot of this type, we try to redraw it as if this is a 3-finger kind of a diagram, but with this finger with a non-trivial braiding which is done in this. So to compute this, we can directly write for any symmetric colors. Okay, if you put any symmetric colors of SUN, we can actually compute the R-colored home fly PT direct. The important requirement is that we need the braiding eigenvalues, which we know, given these braid words which are associated with each of these fingers. And we have also used an alternate method of looking at the twist knots in 2012 with Satoshi Nawata and Zodin Mavia, where we have conjectured the SUN quantum Wigner-6j symbols, and that was, I think, is a very important result, because any arborescent knot you can compute R-colored, symmetric colored polynomial. Of course, by mirror symmetry, you can also compute the antisymmetric invariance. So in that sense, this was a very crucial step, and this input to the quantum algebras, where you need this Wigner-6j, came from the twist knot results. Okay, so that way I find that the knot theory has given an input which was an open problem. It's still an open problem for arbitrary representation. At least for symmetric representation, we have given an indirect way of determining a closed form expression. Okay, using these two, you can compute R-colored, symmetric R-colored or antisymmetric R-colored for any of these arborescent knots. Very, very straightforward, and this gives us so much of data, computational data. Okay, and the other thing which we are mainly wanted to do is, we wanted to write one universal invariant which is dependent on this kind of a tree diagram. This is a shorthand way of drawing it. You can see that there is a 3-valent vertex, there is a 4-valent vertex, there is a propagator connecting these vertex. So there is a systematic way in which each one you can put a finger and a propagator which is a cylinder, and then again 3 fingers. So it's very neat to draw, but what we wanted to do is we wanted to write one invariant dependent on parameters and get an answer, and anybody plugs in those respective parameters can get the polynomial R-colored home fly PT for arborescent knots. That was our aim, okay? And we tried to keep the number of parameters as minimal as possible. But what happened was that we needed at least 7 parameters. Even with the 7 parameters, up to 10 crossings, some of them could not be incorporated. Okay? But this is still a very small number. Okay? So, but most of the knots up to 10 crossings, with just a universal 7 parameter diagram, we can give it to the computer and get the polynomials for any R color technically, but explicit results up to 4 boxes, we had put it up on that website. Earlier it used to be not ebook, but it is changed. I had given that slide in the learning workshop. Okay, so this is also one thing which kind of makes us think that in the light of recent developments on knot quiver, can we also get a quiver which is dependent on such parameters? And these are things which are still exciting, still an open problem. And we have some things on some subclass of these families which I will mention towards the end. Okay, so quivers for such family will be the biggest target, but it looks like. Because I should also mention this arborescent knots, there are quite a number up to 10 crossing, but the non-arborescent takes over beyond 12 or 13 crossing, the number of arborescent starts increasing. So even though the methodology is there for arborescent, we need a methodology for non-arborescent, because if you want to look at many more problems which are open problems like unknot detection, you need to have a handle of finding the polynomial results beyond arborescent knots. Okay, so non-arborescent also we had been learning from the group Mironov, Morozow and other collaborators. There's a method called quantum R matrix approach. There's an eigenvalue method, eigenvalue hypothesis method. There is a highest rate, but each one is okay for number of strands being 3 or 4, but beyond that it becomes even more tedious. And then we mixed and matched our arborescent information to the non-arborescent methods, and we could have a hybrid approach. So we tried to do as much as possible to get the polynomial invariant, but here we couldn't go beyond a finite number of boxes, and we cannot claim that we can get for a large number of braid strands any R colored home fly PT. Okay, there are some works where we had struggled even for 2 symmetric boxes for a 4-strand closure. So it looks like a little tedious approach, but that's that's where it stands. Okay, so this was work with Mironov, Morozow and others, and this was a part of our India-Russia funding which happened for 6 years, I think, 2014 to 2019. Okay, so far I kind of focused on the knot invariants, but then we also know that there is a regular isotopy invariant or in vertical framing or blackboard framing, which are called frame knots, and those play a crucial role when you do surgery. Surgery on frame knots can actually give you different 3 manifolds. Of course, modulo Kirby moves, which I was mentioning it during my set of lectures. Formally, in terms of those knot invariants or link invariants, link invariants can depend on different representations put on the components, and you can also have different framing because they are framed knots or links, and this turns out to be the 3 manifold invariant or the WRT invariant. And this has been worked out when you take the polynomials of these in Q. Q is the root of unity. This will be for SUN or UN, it will be N. And K, coupling constant or K, which is strictly taken to be a positive integer. Okay. So this is the frame where we can connect it to Chern-Simons field theory. And these are the variable change by which you can relate it to WRT. So this is just a summary of what I was talking in the lecture series and learning workshop. Now we get to the interesting issues which was looked by why are these polynomials for any knot, for any representation. So I'm taking the colored home fly PT. We could work it out for mixed representation, but low dimensional mixed representation. But whatever we do, these coefficients are integers. So it's a polynomial in two variable, and the variable A is related to the rank of the group SU and group as q to the power of n. Okay, so this integers was kind of, we all want to know what could be the meaning for these integers. So you need interpretation or reasoning. So this is what I was mentioning, that in around the turn of the century, there were a lot of interesting parallel developments in both math and physics, where one could account for the topological meaning for these integers. So one was this categorification, Konow categorification, which led to further SL3, then Konow-Rosansky developments. But I thought most of you might have seen this, but let me try to take it for completeness. And then the other one is the Oguri-Wafa. So we just review this. There is a way in which I remember in 2009 there was a knot theory school and workshop where Kaufman actually taught us how this categorification can be viewed like looking at as in a StatMech model, statistical mechanical physics model type. So I was very interested, and I do see that there's a way of writing it in terms of all possible states, the invariant for a trefoil, where there are two types of smoothing, A or B, and this is an A smoothing, and the state is given by two integers n and j, where n corresponds to number of B smoothings and j will be related to putting a sign to each of these loops. N plus is the number of plus signs and n minus is the number of minus signs. So it's a very neat way in which we could, for this particular example, ns is 0 because B is 0 and j turns out to be 2. And formally one could write a chain complex with a differential, and then this will be the homology group dimensions. So you can clearly see that we do get a Lorentz series for the Jones polynomial, and with this accounting for the integer coefficients with the sign coming from this additional grading. This additional grading is what takes you from n to n plus 1. So for example, if you take this and do the del, there are 3 possible states, and of course we take the mod z mod 2, where with these coefficients have to be either 0 or 1. If you take this, we can work out what are the values of this dimension for the trefoil. Okay, so this is also there in Kaufman's paper, where we could show that going from here to here, what is the dimension, and we can rewrite the Jones polynomial, or equivalently you can write the minus 1 to the power of n by t to the power of n. So in some sense you call it as a graded Euler characteristic will correspond to t equal to minus 1, will give you the Jones polynomial. Okay, so this justifies, and this is not dependent. Okay, it's not same for, to be different for different knots, and this justifies the integer coefficients. And of course, this I've tried to say for the Jones, but this also has been done by Konow-Rosansky in a different way to account that these have to be an integer, not only for Konow, but Konow-Rosansky and so on. Okay. So as I said, t equal to minus 1 gives the Jones polynomial. So there's some work in Chern-Simons also was done by Agenic, Mina Agenic and Shamil Shakirov, where they tried to refine the braiding eigenvalues. Initially, usually the braiding eigenvalues can be written in terms of that Q variable, which is a root of unity, dependent on Chern-Simons coupling and rank. But then they they tried to introduce a refinement where beta deformation or beta equal to 1 will actually give you back your original Chern-Simons braiding eigenvalues. And of course, the quantum dimensions which are related to Schur polynomials were also modified to be Macdonald polynomials, and they worked it out for torus knots. Okay. So interestingly, there Kohanov, Rosansky, and those polynomials actually matched. So that's the time I was trying to understand whether we could also get the refined the Wigner-6J symbols, but doesn't look like. And then I kind of got from the conference and also from various meetings that it is not that combinatorial to get category 5 invariance or homological invariance in a very simple way. It seems to work for the torus knots. Okay. So, but independently, this kind of led to general, this is what we call it as a Poincare polynomial or super polynomial. Technically, the super polynomial will not reduce to your SLN if you just put A to be q to the n. So there is some subtlety, but let me just take this Poincare polynomial for the trefoil. So this is what I have written it for the knot, which is the trefoil, and you can plot this on a, this is what we call it as a homological diagram, where we plot it on the AQ plane, and there are 3 terms with degrees, the powers of A and Q are mentioned here, and then the power of T is mentioned here. So this is what we call it as a homological diagram, and we can also put in a differentials which takes you from this degree to this degree, so it gets killed. So what remains is only this, and that is what we call it as a dimension. It's one dimensional, and then look at the degree of that one dimensional vector space, and that gives us the Rasmussen invariant. So this has to give you a feel that for every knot, the Poincare polynomial can be given a homological diagram way of drawing it, and this is something which has been useful in trying to generate more quivers, which is something which we are trying to work on, but I'll get back to it towards the end. Okay, so just to put a schematic diagram in this homology workshop, so the main central one for any color, okay, so I showed you for only the uncolored, but that's the Homefly PT homology is what we call, but for any color, you can have a colored super polynomial, and then by differentials you can relate it to the Rasmussen invariance, knot Florer homology, and they are all related in a beautiful web of connections. So this is there in our paper on super polynomials and twist knots. So more you can see. This is the work with Satoshi and Zoden on colored Homefly PT and colored Kaufman also. We tried exploiting these differentials and the gay equivalence of 2 different ranks of the groups for various representations. You could actually come up for some of the twist knots, the colored Homefly Kaufman homology. Okay. Okay, so far is the homological invariance, which I give you a brief overview. Any questions? Okay. So the other direction which kind of fascinates, has been fascinating all of us from, I think, late 70s, 1970s, TUF's double line formalism, where if we take a pure gauge theory with rank n, take UN gauge theory or SUN gauge theory, the claim is that at large n, every gauge field can be drawn as a double line associated with the group index, and then it becomes like a theory of Riemann surfaces. So we do expect that any gauge theory will have a string theoretic interpretation. So this is a TUF's proposal. Okay, clearly, if we take the SUN Chern-Simons theory on S3, that partition function, we take the log of this partition function, which is what we call it as a free energy. The free energy, depending on, technically this is the closed string interpretation. But interestingly, there could also be an open string interpretation with Riemann surfaces with holes and sum up over the holes. So this was the CGH at the topological string amplitude or open topological string amplitude. And the target space, string theory should always have a target space, and the target space turns out to be the cotangent bundle of the S3. Okay. There is a geometric transition at large n where these holes disappear and becomes only the closed string amplitudes. So these are the FGs of the closed string amplitude. The geometry also changes, and that geometry changed was explicitly compared to be the resolve coordinate. It's not obvious, but these have been checked. Okay. So there is a topological string duality which relates deformed conifold to resolved conifold, and the free energy of Chern-Simons has an expansion which has a closed string interpretation as expected for any gauge theory from Tufts double line formalism, and this explicit also we know what is the target space, which is the resolve. Okay, and there is also, you can lift whatever is done in topological strings by taking physical string theories compactified on these cotangent bundle or resolved conifold, and there you can compute certain terms in the low energy effective action. Those are the F terms, and then these will account for you what these FGs are. So it's very interesting that certain terms can be computed from topological strings in physical string theories. Okay, so just to give you a pictorial way of looking at it, in the light of Malachena's duality, you need a gauge theory, and the gauge theory is a coincident, we call it as topological branch, which is wrapped on this S3. And then when you do the conifold transition, this S3 at the conifold point, S3 shrinks to 0, S2 shrinks to 0. But when you do a conifold transition, S3 is shrunk to 0, but S2 is blown up. So in the process, you don't have any gauge theory, but the geometry has changed. Okay, so the side it is the gauge theory, but the geometry is changed where it becomes a resolver. Just like the geometry in Malachena's work would be an anti-de Sitter space, here it becomes a resolver. Okay. So in some sense that in the same setting, okay, we could also put knots in S3 and then see what happens on the conifold transition. So once you put knots here, you make sure that when you do the conifold transition, there is going to be some kind of a probe brain to keep track of the knot information. So this was a work of Oguri-Baffa. Okay, so take a 3-cycle LK, because this is a cotangent bundle of S3. You can take a 3-cycle where the 3-cycle intersection with the 3-sphere is going to be along the knot. These are called sometimes as the conormal bundle. And then wrap some number, need not be the same as n branes, but you can wrap m deep branes on LK. And then look for the open strings on the coincident part of it and find the expectation value. This is what we call it as the Oguri-Baffa operator. And this U and V are the holonomies around for these knot, which we are going to consider in S3, and this one is in the 3-cycle LK. Okay. Okay, after conifold transition, you will have residual information encoded in this holonomy V, and essentially this should give us an open topological string amplitude expansion. So explicit working was done for the unknot, and then they proposed a conjecture that these are what we call it as a reformulated invariance. For fundamental, it turns out to be home fly PT, and these have to be strictly integers. Okay. Of course, these nowadays we call these integers as LMOV, and this counts the number of intersecting D2, D4 brane, where we should see the D2 brane with bulk charge Q and spin S, and these are going to be in the presence of M D4 branes, where you wrap it on LK, and it is also ticking out in this uncompactified R2 spacetime. So this is what you will see in the physical string theory. Okay. Okay. So this justifies the integers as counting the D2, D4 branes, or we call it as a BPS states. And what is difficult is, from first principle within topological strings, to find these integers. This is the way it was done for a knot, and also for some simple torus knots. This deriving it within topological string context looks difficult, but what we can do is that this reformulated invariance involves the knot invariance of all possible representations up to this representation. So we could actually verify whether this conjecture holds for any knot. Okay, so this is something which we did with our results. We validated the integrality structures of reformulated invariance. So those were the times when not much was known about the polynomial invariance for non-torus knots, and that was the first instance when we could actually verify and validate Ugriva-Farr conjecture is correct even for Swiss knots. Okay? So this is something which I think was based on our colored home fly PT for many knots, which I had done with my advisor in '92. So that was really useful to verify this. Then Gukov, Schwartz, Schwaffer in 2004 came up with further grading. Just like if you remember, there is a additional charge index besides Q and S. And this additional charge index becomes meaningful if you look at, there are actually two U1 symmetries. If you see it from the 2A theory lifted to M theory, where you can, the top net space allows for, when you do a rotation on the circle, you can see that the top net coordinates Z1 and Z2 can be, you can do two gradings, both T and Q. Okay. So in some sense, the two U1 symmetries are already inbuilt in M theory, and they propose that such a LMOV integer could be having one more additional categorification possible. Okay. And they worked it out for various examples, and they matched well with Kohanov-Rosansky homology. So essentially, the D's now have an interpretation. Okay? So they count the number of M2, M5 branes, and they are candidates for SLN homology. And I said that SLN and the home fly PT homology are up to this differential. So you have to act the differential, and whatever space is left will be what we call it as an SLN. Okay. So this is 2 grading, but there are 3 gradings here. And the BPS, the counting of these are the BPS states, the counting of these for every knot will be actually accounted in this homological invariant. Okay. Okay, so far, whatever I was trying to say, I looked at the validation for ambient isotopy invariance. But technically, we should be able to do it for even frame knot invariance. So frame knots or links, you can extend the number of components by putting an index alpha. So there are R components. Or you can also give these invariants not just as an invariant of ambient isotopy but regular isotopy, and that forced us to go from SU2 to SUN to UN. Okay, so this is one modification which is important, that the invariance for frame knots, of course it will reduce to, for the frame knots it will reduce to, if the framing number is 0 then it will reduce to the SUN, but in general we need to write a UN invariant with the UN charge specifically chosen as the total number of boxes in these representations. So this has been this has been, this was kind of looking ad hoc, but then these conjectures cannot work without taking these invariances. Okay. So then the conjecture can continue for even frame knots and frame links, where these coefficients can be interpreted as, they are integers and they can be interpreted as BPS counting. Okay. Okay, so once I have some handle on how to look at frame knots within topological strings duality, I wanted to use this information into writing the free energy for other three manifolds. Okay. So Chern-Simons partition function or WRT invariant, we can write in terms of surgery of frame links is what I said, the Le Courrish. So formally the expression which I have, there is a way in which I could, if there was no framing or there was no link, I don't need to worry, there is no difference. It's just the SU and Chern-Simons partition function. But if I am looking at surgery of frame links, I will get a new three manifold which I know how to write in Chern-Simons theory, and then because these are done in the topological string context at large n, there is a leading term and there are sub-leading terms. Okay. So the probe brains which was there, I have to also take expectation value if I want to look at, because I don't need open topological string amplitude, I have to sum up all those holes to get a closed string partition function. So there the probe brains have to be, need to give some expectation value, and we made a choice. This we don't have any reason, unless we make this choice we cannot relate it to the Chern-Simons partition function on any three manifold. So this we did, and interestingly we substituted this, and then this expression turned out to be the leading term in the free energy of Chern-Simons partition function. Okay. Now the question is, just like the way Gopakumar Baffa had got log of Z of S3 to have a closed string interpretation, this expression does not look like any closed string interpretation. But we wanted to use Oguri-Baffa information of how these Fs are written, see whether we can bring it to that form. Okay, so this was a challenge, and that will give an indirect meaning what surgery means in the topological string context. So we could rewrite, so the n's are the LMOV integers, but you can rewrite it by putting a hat n, which is called as a refinement with q minus q inverse to the power of 2 g minus 2. So we can redo this, write the leading free energy of Chern-Simons partition function on any M3. We could use the Oguri-Baffa conjecture and rewrite it in this form. Okay. There are some subtleties. We need these powers of lambda to be negative, that's the way to interpret it, and integers, and we have to choose p's not anything but something which is even numbers. So we need to do for a subclass of those links, we could rewrite it in this form. Okay, so I'm sure many of you who have been working on Gromov-Witten invariants and Gopakumar-Vafa integers will realize that these are integers and you can convert this as a gs to the power of 2g minus 2 with rational numbers which are the Gromov-Witten invariants. Okay. So in some sense that we got a closed string interpretation for some subset of framed links. Okay, I'm not keeping track of the time.
We still have more than 15 minutes, but please include time for questions.
Yeah, sure. Yeah. Okay, so this is what we achieved. Because we don't have the information about the target space geometry. They were able to say that it is a resolved conifold, but here we don't have any information. Of course, we have these integers. Probably some of you might be able to help us for some simple examples what this would be the target space geometry. So given a set of Gopakumar-Vafa integers or Gromov-Witten invariants, probably the geometry can be what the geometry of X is, not resolved conifold, but what it is can be figured out. Okay, but still it's puzzling because this one which we have done is just took the WRT leading term and then the log of that turns out to be a closed topological string partition function with one Kähler parameter because it doesn't have more than. There were also parallelly around that time there were works on length spaces, and it appeared that the partition function, the Chern-Simons partition function, which is also the WRT invariant, should be over all the saddle points. Okay, now we even have more information that these saddles could be weighted from the resurgence of complex Chern-Simons. So this is over all saddles. And what Tooft proposed was around the saddle, not for summed up over all the saddles. Okay, so this was the proposal that you do a perturbative expansion around the minima or extrema, and they should have a closed string expansion. Okay, but what we have is that the summed up value is having a closed string partition function, and we have been little bothered, and we don't know how to understand what these NGMs will mean because this is not the interpretation we have. Okay, so the other variants besides SU group and UN group, we could also use systematically our SO invariants, which are the Kaufman and colored Kaufman, and look into the topological string context where you will have an orientifold present. And then once there is an orientifold, you can have twisted sector and untwisted sector. So there will be an oriented contribution and an unoriented contribution, even for the free energy. Okay, and then this was done by Sinha and Vafa, and the same Oguri-Vafa extension, putting in Wilson loops will also force you to have an oriented contribution, unoriented contribution. So with my student, I think in 2005, using our knot invariants, we conjectured or we explicitly verified that there is an integrality property for even the colored Kaufman up to some low colors. Okay, but what was not clear is how to split it up into oriented contribution and unoriented contribution. Okay. So then, interesting work by Marino where you will have to forcibly put a composite representation. So composite with R being fundamental and S being fundamental is what will give you an adjoint representation. And then we redo the calculations and they will give you the integrality property. So these essentially will require UN invariants to compute and find out what these are. So this is also to be viewed as two deformation of the Lagrangian submanifold, which we were looking at the conormal bundle where you do a slight deformation plus or minus epsilon, and then they are related by orientative folding action, which forces this composite representation, is the theme of Marino's work. But then we verified that his argument of integrality structure works for many knots. Okay. So that was work with Chandrima, Paul, Ravina, sometime in 2010. Okay, and various results on the arborescent knots also in mid 2015, we were able to verify the integrality properties. Okay, so once we have the H, we could also get the unoriented contribution. Those we could do up to 2 boxes. I don't think we could go beyond 2 boxes. Okay, so the last few minutes I'm going to try and tell you in a nutshell. Of course, you listen to Fedre and also Elder on details. So this is a very shorthand way in which you could get this as a plastic exponential involving the LMOV invariants. And these summations are over only the symmetric representations. Equivalently, for every this generating function, you can get an equivalent form involving a quiver generating function, Qk for every knot, where these x is replaced by a boldface x with each of these components turning out to be related with some weighting factors. If Ni is 1 for all i's, then they are the thin knots, but otherwise you need to make this modification. 942 you need to make a modification. And you could rewrite them in this fashion, and this is what I call it as the quiver matrix, and the dimension of this quiver matrix is I and j will run 1 to m, so it is m cross n quiver matrix. So these two are equivalent, and this series can also be written as a plastic exponential of Donaldson-Thomas. So these are integers. So this kind of gives an indirect proof, or proof that LMOV for symmetric representations are integers. Okay. So there it was not obvious from the Oguri-Waffa conjecture, but then the proof is very neat in this way of looking at it. But this also brings in one more question, that for every knot, you should find at least one quiver. So there are a lot of works where there are many, it's not 1 to 1 onto, there are many knots, and the number of nodes being same are on a permitohedra, but you can have number of nodes being different and so on. So there's a lot of work which I'm sure we'll hear in the next 2 lectures. For the simplest example, for the homological diagram, if you remember, the homological diagram had 3 nodes for the trefoil, and you have at least a quiver matrix with 3 cross 3 matrix, and this is a quiver diagram associated with the trefoil. Now bringing back my question which I asked, can we find quivers for a knot family? If not the biggest universal family, at least some subclass of families. So this is what we took it up as a double twist knot, and of course there's this reverse Melvin, Morton, Rosansky approach, which is done by Bashish, Jankovsky and Piotr, which helped us to go through this systematically. The procedure involves inverse binomial expansion and rewriting it in a cyclotomic form, where there is a knot dependent piece and a knot independent piece. This is something which we have not been able to manage. Like we were trying to do this for weaving knots. I don't think we have managed to get what is the C tilde k, and that is the challenge. Finding the C tilde k is a challenge. Once we know this, then any R colored symmetric invariant is known, and equivalently using this, you can also work out the quiver form. Okay, so double twist knot which had a very interesting property. The Alexander polynomial written in this variable x. I have not defined what that x is, but probably in the previous slide I have said this. This is the x. It has some nice linear property, okay? And this helped us to go ahead with doing this binomial expansion and trying to write using this reverse MMR method, conjecture a generic structure, and the structure of the quiver was having a dimension of 4MP plus 1. Okay? So this is the work with Vivek, Sachin, Aditya, Bhavani and Siddharth. Recently got published, so we have put in explicit data for these twist knots. Okay. Okay, so let me try and say a couple of problems which we are trying. We hope we'll have some results. Essentially, the diagram which I drew for the arborescent with many fingers, 4 fingers and 3 fingers. So specifically for the 3 finger, the Alexander polynomial seems to have a structure similar to this. Of course, this coefficient is dependent on the parameters of crossings which are put in each of those fingers. Okay, so we want to see whether we could write or conjecture a format for the quiver matrix structure for 3 finger pretzel family. Okay. Of course, papers on permutohedra, unlinking and linking, some of them we'll listen to. There were some talks by Dimitri lecture series. Suggest that we should have some ideas to attempt this pretzel family. Why pretzel family? Other families also. And also other interesting works on these homological knot complement 3-manifold invariants, and it's not clear whether we could extend this, whatever procedure to generate for the family can also be used from the FK for FK quivers to that family. So some things which we have some ideas. Looking at the homological diagrams, the growth of the homological diagram, but it's still, we hope we'll have something concrete. Other problem which was mentioned was Sachin's work on the Z-hat or homological blocks is only dependent on Lie algebra, whether this is going to continue for other SO, and whether we could also do refined versions. So these are things which one should pursue. I should also say, in the light of machine learning developments, we do need a very high computing facility if you want to go to large number of crossings. Even though we have a methodology to give a formal invariant, then maybe it will be useful to do unknot detection. Some work we have already in progress on looking at the volume conjectures. Kashev's conjecture, whether it can be done for fractional, some rational values of k, but this unknot detection is still an open question. It will be probably requiring heavy duty computation. Thank you.
Do you have questions? Pedro?
Yeah.
Can you say again for which family of 3 manifolds did you compute the Gopal-Kumar-Vafa invariants from surgeries?
Which family of 3 manifolds?
Yeah.
So there are these lens spaces. So lens spaces P comma Q. If my memory is correct, I think we worked it out for 4,2 is my memory. And there are some more examples, trefoil and other things also we worked it out. So trefoil with framing 2 will go to a Poincare sphere. So a couple of examples we have worked it out where we have listed those integers. But there was one more that we had to do an analytic continuation. The lambda to the power integer fixed for me the framing numbers. And I also have some things where I needed it to be always lambda inverse, so I had to do an analytic continuation of lambda to lambda inverse in some of the terms. But after I do that, I get those integers. But it's one Kähler parameter. Unlike if you had done the local, say let's take the level space, the local one, this should involve M d dot t kind of. There will be a t1 and t2, right? So you will have a d1 t1 and d2 t2 if you are doing even the lens space locally. So there will be a local z2. You will have that, right? Because S3 mod Z2, this one is S3 mod Z2. So, but we are not able to get that information. Somehow that summation over C seems to have taken care of this information. So I could try to write T1 as dependent on 2 pi n1 by then you can try to write this as n1 plus n2 and call that as n. But that n1 plus n2, we tried all these things at the large n, whether what will be the dominant contribution to somehow figure it out. It'll be good if somebody can help us out, sort this out, and see what the geometry is. Yeah.
After you get closed, is Gopakumar-Vafa invariant?
Huh?
Can you get this closed invariant?
Closed.
Gopakumar-Vafa?
Yes.
Did you try to get anything on top? I mean, the open ones in some way? Is it possible?
Yeah, I don't think I can. I only use the Oguri-Vafa procedure to write, but in the case of Gopakumar-Vafa, we knew what was Z of S3 explicitly. We could write that S00 as an expansion, both with genus as well as the wholes. But such an expansion, I don't think I have a clarity. No. But technically, if we do that, that will be a T star of that. That's for sure. But I don't have the open topological string amplitude.
So you mentioned many methods you use to compute color Humphrey-Fitty polynomials.
For non-arborescent, yeah.
Sorry?
For non-arborescent.
Yeah, for non-arborescent.
Yeah.
Do you know if they could also be used for this? Or is it easier, doable to see these quivers arising in those methods?
See, there we are not looking at the method by which the quivers will arise. We are trying to see, using the invariant, whether we can recast it by looking at the Alexander polynomial or by looking at the homological diagram and so on. But I don't per se see how a method can actually give us some insight on the
So, for example, this 6J Wigner symbol is still not. On one side it gives it not invariance, but on the other side you also have this not squares correspondence. So is there a direct relation between the two?
No, it's not that obvious at least. It's a messy expression, so I cannot even. In fact, this question I can say in a different fashion that I know certain invariants evaluated by some other method for mixed representations, like torus knots, for example. There are two ways in which you can compute. One which involves the Wigner space, and the other one where you know how to compute the colored home fly for torus knotting. But even there, to extract the Wigner 6Js is not an easy exercise. Yeah. It'd be good if some other insight can come to fix the Wigner 6J in general, because the Wigner 6J in general will involve R1, R2, R12, and then you will have an R3, R4, and R23. Okay, so this is what we require. But what we can do is only when these are symmetric or conjugate of symmetric. You know, so in some sense we are symmetric with. It could have different representations, but it has to be symmetric and conjugate of symmetric. Okay, so there's some requirement where we could find it, but in general, to extract this information looks like a very tedious exercise. And the good part in the case of SU2 is that all the symmetric representations are also there in SU2. Right? All symmetric are in SU2, so we can actually see when n equal to 2, we get back the Kirillov-Reshtkin. This doesn't happen for mixed representations. They need some work, but it's not very visible right now.
Any other questions? If not, let's thank Rama again. And we will meet again in an hour and a half, the night for Pietrost.